Enhanced EIGRP features and operation. Cisco vastly improved its proprietary EIGRP protocol with Enhanced Interior Gateway Routing Protocol, or EIGRP, by delivering a hybrid algorithm that uses elements or components of distance vector protocols and link state dynamic routing protocols as well. Now, although EIGRP can be used to route IP, IPX, and AppleTalk information, this nugget focuses exclusively on IP routing with EIGRP. In this nugget, we're going to cover a variety of the aspects of the features and operations of the enhanced EIGRP protocol. First of all, we're going to look at the many features and characteristics of the EIGRP protocol, and there's a lot of them. In addition, we'll look at the important terminology and concepts that you must conquer in understanding and deploying this EIGRP protocol. Next, we'll show you how to simply configure the EIGRP process on a router and quickly build a neighbor table by leveraging EIGRP's automatic adjacency discovery process. While we're on the router, we'll take a look at the neighbor table and break down the components of that data structure. Also, we'll use that opportunity to configure the hold time on an EIGRP router for certain circumstances. In addition, we'll look at the topology table, which is just another of 3 different tables or data structures that EIGRP runs. And then finally, we'll take all the information we learned and look at an overview of the EIGRP discovery, selection, and maintenance process. Enhanced EIGRP, or EIGRP as I'll call it from now on, is really a hybrid dynamic routing protocol in the sense that it uses distance vector properties when finding the optimal path on a network, but it utilizes link state properties in discovering neighbors or peers and managing changes in its topology. And EIGRP is based on the EIGRP Cisco compatible protocol, so it's an excellent protocol if you're scaling up your EIGRP environment. It makes several improvements and enhancements over EIGRP, and I want to take a few minutes here to look at some of these. Obviously, it's great for building a scalable solution if you're using EIGRP, especially if you're in an all Cisco hardware environment. If you are looking at multiple vendor compatibility, you might want to consider OSPF instead of EIGRP for a growing or scalable environment. Probably the most important enhancement to EIGRP is the fact that you get the benefit of reduced bandwidth usage or utilization, in the sense that EIGRP, like OSPF, uses a multicast address as opposed to broadcast packets to propagate most of its traffic, and that's going to give you better utilization of bandwidth. EIGRP also allows for route summarization and allows you to build a hierarchical IP addressing scheme. It's also a good protocol if you want to do a technique called route redistribution. In other words, in the interim or during the migration process, as you're moving from let's say a RIP to an EIGRP solution, or you decided to go from an OSPF open scalable solution to a all Cisco EIGRP solution, you have the benefits of redistributing or injecting routes from one routing protocol into another, for example EIGRP. Also, it uses a algorithm called dual, and let me put my little M here, I left an M out, the DUAL, or diffusing update algorithm, which offers a much faster convergence over the distance vector techniques used by EIGRP or RIP version 1 and 2. EIGRP, like OSPF, also has a topology table, so it has a picture of the internetwork. It performs all the routing computations, provides a loop-free environment, and then it will ultimately inject this information into the routing table. And these are just a few of the advantages, but one of the main advantages here is the fact that EIGRP uses incremental updates as opposed to sending the entire table like RIP and EIGRP does. It will just send an incremental update and that's a big advantage. It goes back to, again, this bandwidth utilization. And you know what? There's even more benefits, and we've got another slide here to look at. Benefits of EIGRP. EIGRP functions over a local area network like Ethernet or Token Ring, as well as popular WAN technologies, for example, a lease line connection or the ever popular frame relay. We mentioned that it supports route summarization, and that will lead us to supporting variable length subnet masking, VLSM, and supernetting or CIDR. Its metric is, instead of based on hop count, the EIGRP metric is based on a couple of metric values, one of them being bandwidth, the bandwidth of the link, and a mathematical delay. And that's just 2 of the 5 possible metrics that we can use. Those are the 2 that are used by default. We'll look at all of the metrics a little bit later on. EIGRP also balances up to 6 equal or unequal paths. So that's another advantage of this Cisco proprietary protocol. In addition, EIGRP provides support for multiple routing or routed protocols. For example, TCP/IP, which is what we're concerned with here in this nugget, IPX, and AppleTalk. So it supports multiple routed protocols. It's also easier to configure and operate versus OSPF, which is a little bit more complicated. So that's one of the advantages of EIGRP, is it's a little bit simpler, and if you're coming from a IGRP environment, it's totally backward compatible, and it's a pretty smooth transition. So a lot of features and characteristics and advantages of the enhanced EIGRP routing protocol. Okay, now that we understand the characteristics and some of the features of EIGRP, let's look at the EIGRP terminology and concepts. And there's quite a bit of them, and we're going to use this diagram here to explain some of these. Now, the first one is the concept of a neighbor. And a neighbor is just simply 2 EIGRP routers that are connected and exchanging update information. This can be over an Ethernet here, or perhaps you've got a router E connected to another router over a WAN connection. So those are neighbors. Now each EIGRP router is going to store a list of these adjacency relationships in what's called a neighbor table. Now also realize that a router is going to have a neighbor table for each supported routable protocol. What I mean by that is this: if we're running IPX, SPX, and IP, and AppleTalk, each one of these routers is going to have an individual neighbor table for each one of those routable protocols. So it'll have a neighbor table and it'll have a routing table for each one of those protocols. Now the multicast data packet that's used to discover your neighbor and to manage these relationships is our old friend, the hello protocol, the hello packet. If a router wants to know information about a link that's gone down, about a neighbor path that it has lost, it's going to send out a data structure called a query. And in response to that query, a router is going to send a reply to the query, and then of course an acknowledgement is also going to be made with the hello packet. And it's usually not data, it's just an ACK packet, and ACK. Let's continue with our terminology and concepts here with a new diagram. We've also got what's called a hold time value. The hold time value is the amount of time or the duration that a router is going to wait for a hello packet from a neighbor before it says, you know what, my neighbor is down. And we'll look at that value a little bit later on. You can modify that value as well. Now we've already mentioned that these routers have what's called a neighbor table. We've also established that these all have what are called routing tables. There is a third table in EIGRP that is called the topology table. The topology table, TT, is a data structure that contains all of the learned routes to destinations, and these are maintained for each routed protocol. So we've got 3 types of tables in EIGRP. we've got a neighbor table, a routing table, and a topology table, one of those for each routed protocols. Therefore, if we were running IPX, IP, and AppleTalk, each router would store 9 different data structures or tables. And again, that's a lot of overhead, but keep that in mind. Okay, a couple of other timers. You've got what's called the SRTT, and that is the smooth round trip time. The SRTT is the amount of time it takes in milliseconds to transmit a packet reliably to a neighbor and to receive from that neighbor the response as an acknowledgement. So that's the smooth round trip time. There's also another value called the RTO. The RTO is the retransmission timeout. RTO, retransmission timeout. And this is the amount of time that a EIGRP router is going to wait before it retransmits to a neighbor. So a couple of values there. SRTT, smooth round trip time, and retransmission timeout. Okay, bear with me for a second as I draw a couple of more routers here to explain our next concepts. Need a couple of Ethernet connections coming from router C and router E, and then a WAN connection to a router, and we'll call this router X. This next term is very important, and the term is successor. Realize that the topology tables, TT, are going to have all of the possible paths to all of the destination networks in the EIGRP internetwork, in the topology. What it eventually ultimately injects into the routing table is a single successor path, the most feasible path, the lowest cost path as far as bandwidth and delay goes, to a destination. So I may have several possible paths in the topology table from router A to router X. However, only one successor is going to be injected into the routing table, and that's the one that represents the best path to the destination. Now, also what you have are kind of backup successors, and these are called feasible successors. They aren't the successor, but it's a feasible proposition that they could become the successor if something happens on the best path to that network. A feasible successor, and there can be several of those, will ultimately get injected into the routing table. And we're going to look at these concepts a little bit later, but these are important things to realize as far as EIGRP terminology goes. So, successor, feasible successor. Now, the actual metric to a remote network, for example, from router A to router X, this is known as the feasible distance. The feasible distance. This is a mathematical value of the total bandwidth and delay values across all the routers from router A to this router over here, network X. Okay, let's go up one last time and get a new diagram here for our last few terms. The usual operating mode of a router, mode, M-O-D-E, is the passive mode, and that's the normal activity where it's looking in the routing table to find the route to a destination network. However, it may go into what's called the active mode, and this can happen if the router has newly been added to the network. There's been a change of the configuration on one of the other routers or an added router, and there's a change in the topology, so there's recalculation going on in the topology table or changes in the neighbor table. Then the router is going to be called in active mode. This is really the time period while a router is querying its neighbors to find out information regarding network path information due to changes in the topology. Now, what you don't want to happen is what's called stuck inactive, and I think we can figure out what that means just by virtue of what active mode is. But stuck inactive, or SIA, means that a route that's been abandoned or it's been cleared out is taking too long for the EIGRP query to be answered. And so if it's sitting there stuck in active mode waiting for an answer to its query. And this is something we want to try to alleviate this problem, and we'll look at this a little bit later on. But again, 3 modes. The most common mode is the passive mode. Then for a brief period of time a router will be in the active mode, and then of course you've got the stuck in active mode. And again, this will show up in your tables as to what mode you're in depending on what command you issue at the iOS console. Okay, let's reinforce the EIGRP terminology and concepts by looking at the discovery, selection, and route maintenance process. As I mentioned, EIGRP routers use the hello protocol or hello packets for the neighbor or peer discovery process. This is done using multicast address 224.0.0.10, so it's multicast out to all routers, and if they're running the EIGRP routing process, they're going to listen on that multicast address and they'll respond accordingly. And this is how they discover neighbors. An adjacency relationship is going to be established. This is a formal relationship between 2 EIGRP devices, and the goal here is to exchange routing information. We saw the 3 different types of tables previously in this nugget. Once an EIGRP router gets a hello packet from a router in the same autonomous system, it's going to establish an adjacency or neighbor relationship. Realize that EIGRP adjacencies must occur within the same autonomous system. So this makes this an interior gateway protocol primarily. So neighbor relationships are not going to be formed if the devices are in different autonomous systems. Also, EIGRP uses the primary, not the secondary address on the interface to build its adjacencies. So the primary address on an interface, not any secondary or sub-interfaces. Now the actual hello packet interval depends on the type of media being used. But if you're on Ethernet, token ring, fiber, or a faster WAN link, a hello packet's going to be sent every 5 seconds. However, they're also generated every 60 seconds on slower links. For example, if you've got an ISDN basic rate interface, maybe point-to-point or multi-point serial interfaces, they'll happen every 60 seconds. Okay, we mentioned earlier that the neighbor table is basically the information that's learned from the contents of hello packets stored in this table, and EIGRP uses multicast hellos for discovery and updating or sending route updates. Now, before we can even get to the discovery process, we have to go ahead and configure our routers for EIGRP. So let's go ahead and go to router A and do that right now. So let's bring up our hyperterminal. Okay, I'm on router A. I want to go ahead and get into exec mode, and of course I want to configure my router. The first thing we're going to do is we're going to say, look, we need to get an EIGRP process going here. And if you remember from your CCNA days, or if you haven't gotten familiar with your CCNA information, go back and look at those CCNA CBT nuggets. But I'm going to go ahead and do router EIGRP. Then I need an AS number, and we're going to all be on AS number 1. Then of course I'm going to advertise using the network command which networks are connected to this router. So I've got 192.168.1.0 network. I've also got a network 192.168.2.0 network. And of course I've got a 172.16.3.0 network. So advertise my networks and go to each one of my routers, router A, router B, router C, around my entire LAN, and configure them all with the same AS number, EIGRP1, and of course advertise the networks that they're connected to on their various Ethernet and serial interfaces. So I'm going to exit out of this mode and get back to, could have done Control Z. After a few minutes, we're going to be able to run the show IP EIGRP neighbors command, and we can now start to see our neighbor, the entries in our EIGRP neighbor table. And I've only got one neighbor connected and running right now, but it's on serial interface 0 on address 1.2. You can see the hold time value here shows up as 13, and this value is going to be somewhere around 15 seconds if it's a faster WAN or LAN interface. 15 seconds because it's 3 times the value of the hello packet. So around 3 times the hello packet is 13, 14, or 15 seconds. If this were a slower WAN interface, which is a hello packet value of 60 seconds, I mentioned that earlier, then on a slower WAN interface, we would see a hold time of 180 seconds. And again, the hold time value is measured in seconds and represents the amount of time that a router is going to wait to hear from its neighbor before it declares it down. And you can also see over here uptime values, and of course here's that smooth round trip time and RTO that I mentioned earlier. Okay, I'll quickly pop down to interface configuration mode for interface serial 0. I can actually manually configure the hold time value on a per interface basis using the IP hold time EIGRP command. And I'm going to do that here on interface serial 0, and realize I can do this on Ethernet connections that I may want to, or faster connections. I may want to increase the hold time if I feel pretty good about the stability of the connection. I don't want it to go into putting a downlink prematurely, and that could cause topology changes and subsequently cause convergence and overhead on my network. If I feel confident about a slower serial connection, I may want to decrease that hold time from 3 minutes or 180 seconds down to something smaller. So let's say, for example, on interface serial 0, I want to modify the hold time. So I'm going to go hold time, and I want to use hold time EIGRP, and then make sure I have the autonomous system number 1, and of course I'll make it 60 seconds and bump it up from 15 to 60 seconds to modify the IP hold time on an interface by interface basis. Now, one other quick thing I want to show you before we go back to look at some other topics is this. If you run the show IP neighbors or show IP IGRP neighbors command, pardon me, and you get this entry, notice the queue count. The queue count is kind of important to look at, and if on a regular basis, if you look at this value and the queue count is anything greater than 0, and again, the queue is really just what's waiting in line, what packets are waiting in line to be sent. This is a value greater than 0 on a regular basis. You may want to take a look at your network and your network design. You've got a possible congestion issue here, and maybe want to look at maybe increasing some of your bandwidth. So there's the queue count there in the show IP IGRP neighbors. As EIGRP routers go through the discovery process and discovering new neighbors and requesting and replying and getting acknowledgments from these new neighbors, it begins to construct a table which we mentioned earlier as the topology table. And the topology table, I'll just make a little representation of that topology table here, and we'll look at it on a router in a second. The topology table contains all the routes that it's gathered from its neighbor routers, and this is going to include things like the feasible distance, the FD, and the feasible distance will be an integer number that represents the lowest cost route to a particular destination. Now, how does it determine this distance? EIGRP uses its metric, which is a combination of several different metric values. And the ones that it uses by default are bandwidth and delay. Bandwidth and delay. And this, of course, is just like the IGRP protocol, bandwidth and delay values. Now, in addition, it can use additional metrics, which are reliability, load, and the MTU, or the maximum transmission unit. And it can combine all these metrics for more complex environments. Generally speaking, however, most of you will always just simply use bandwidth and delay, and it's really quite rare to find tweaking these values of these constants. So the metric that the router actually will use will be the sum of the best metric that's advertised by each neighbor and the cost to reach that best neighbor router. For example, from router A to router X over here. A topology table also indicates if the entry in that table is in the normal static mode, or passive mode, or is it in a active mode. And we mentioned those two modes earlier. A route is passive if the router is not performing any recomputations or calculations on that route. Now we can also go do the show IP EIGRP topology command in our router, and we can look at the routing table. We'll do that real quick. Let's bring up a hyperterminal here. Okay, let's go back to router A. And again, I can take a look at the command on my router. I'll do show sh IP EIGRP and then topology. Now, of course, I've only got one connection here, but I want to talk mainly about these different codes, and we'll talk about some of the other items that you may see in here. Now, what you're going to find, first of all, is you're going to find an entry. There's only one successor. There's only one best route to a destination. So you're only going to, you may, if you have multiple connected networks here, you'll have a successor for each one of those particular network connections that are in your topology table. So I could have 3, 4, 5, or more successors in here. Now there's feasible successors that are stored in another table, and basically those are ones that are on standby in case my successor route goes down. It can recalculate and use one of those feasible successors to ultimately add that into my routing table. The feasible distance is a mathematical value based on the metric we just talked about, bandwidth and delay. And of course, the feasible distance is going to be the one with the lowest value. The successor will have the lowest FD number. Now let's look at these codes real quick. You've got passive, active, update, query, reply, and reply status. I've only got one entry in here, and it's just basically this passive entry that I have for this particular connection to another router. But these codes, for example, if it has an A next to it, means it's an active one, and it means that presently EIGRP calculations are being performed for that particular destination. If it's got a U next to it, or update, that means that an update packet was just sent to that destination. If it has a Q next to it, it says when you ran this EIGRP topology command, that basically a query packet was just sent to that destination. It's in that process. And if you've got an R, it means reply status. So these are all different codes to show you the status of your entries in your EIGRP topology table. And again, it's just one of several tables that we have available to us in EIGRP. Okay, so let's go back to our diagram and talk more about the EIGRP selection process. Now in a larger environment, EIGRP can choose up to 6 routes, and as we mentioned earlier in the nugget, they can be equal distant or unequal routes. And you're going to have one primary route, and that primary route will be the successor, and up to 5 backup or feasible successor routes per destination, and it places these into the topology table, and ultimately that gets moved into the routing table. Also, similar to the OSPF protocol, EIGRP also supports internal, external, and summary route information also into those tables. Now I mentioned the EIGRP metric being basically the same as IGRP. There is one difference. whatever value you had, metric value you had for EIGRP, just take that number and multiply it times 256. So the EIGRP metric times 256 equals your EIGRP metric. And again, that's bandwidth and delay. Bandwidth is, again, the value that's the smallest bandwidth between the source and the destination. The delay is the collective delay amount of the interfaces along the path. And then, of course, you've got three other metrics that we're not going to get into detail on, but those are reliability, load, and the maximum transmission unit. Okay, so let's go ahead and overview this overall selection and maintenance process with a fresh screen here. Now, let's say we have router B. EIGRP is going to receive an initial multicast hello packet from router A. And again, this is going to be on 224.0.0.10 that all of these EIGRP routers are listening on. Now, unlike OSPF, your connected EIGRP routers are going to form this peer or this adjacency state after they initially exchange hello and update packets with each other and acknowledge the receipt of those packets. So once A sends packets to B, this process will then reverse, and router B is going to send update packets back to router A that contain its table information for its connected routers. Maybe it's got other WAN connections, of course, and other routers besides this one LAN. It sends that information to one another, and they return ACK packets back to each other. And when finally both of the routers have incorporated all of their neighbors' routing information, they start to use that dual algorithm to select the successor and up to 5 feasible successor routes, and then they inject them into the topology table, and then eventually that gets injected into the routing table. And then reply packets are unicast packets that are sent from one router to the other in receipt of query information. And again, we're looking at routers that are generally in either a passive state, just doing their thing, or they're in an active state when this selection and maintenance process is taking place. In this nugget, we looked at the many features and enhancements of the EIGRP protocol. We also looked at a variety of terms and concepts dealing with the different kinds of tables in EIGRP, the different kinds of messages like hello, query, and replies, and values like hold time, SRTT, and RTO. We also took a look at the neighbor table, and we looked at a quick configuration of our Cisco router and other values. We configured the hold time configuration as well. We also broke down the topology table and the different codes and values in the topology table, and then finally one last overview of the discovery, selection, and maintenance process in EIGRP to prepare us for the next nugget. I hope this has been informative for you. I'd like to thank you for viewing.